Happy Monday, honors chemistry. Hope you had a wonderful 3-day weekend. I, as you will hopefully remember, am off onto PSSA proctoring for the entire week, as far as I know. If I can be back on Thursday and Friday, that has happened in the past from time to time. I will be, and I'll let you know that. Come to think of it, as I'm recording this, I don't think I got rid of your class connect yet. So if you happen to see those, because I still forget, there will be no class tomorrow. We're not necessarily taking formal attendance either, so um, just a little ditty on that. We're studying today the States of Matter unit, lesson 14, that is about phase diagrams. And in the lesson on phase diagrams, we're mostly focusing on states of matter, really, which is the title of the entire unit, right? But up until this point, we've only talked about gases. You can see here that we're looking now uniquely at water. Water is special in that in our purview of temperatures, the temperatures we regularly access, we can see water form 3 different phases. It has ice, liquid, and water. I'm sorry, ice, liquid, and water vapor. So what I've tried to show you here is just snippets. We're going to look in greater detail at actual simulations of how molecules behave. That's one of the really big ideas we want to take away. The fact that molecules behave differently as you access different states of matter or different phases of matter. And in order for them to change, phase diagrams show the change or where things will change or how they will change. It's important before we understand phase diagrams to understand states of matter and what they are. So when we go from one phase to another, it's important to understand that energy accompanies that. What we see here on the left is our ice cube block and its molecules behaving very different than those in a water sample, in a glass of water, for example, or even in a water vapor gas like steam that might rise from your shower. We're going to look at these in a lot greater detail, but everything we learned today comes back to this. So this is your fundamental idea that you want to focus on and be able to understand going forward. In terms of specific goals for this lesson, number one, you want to be able to do that. Explain the molecular behavior in various phases. What happens in molecules of a solid, of a liquid, and of a gas. It's an excellent essay question for open-ended question for your test, for example, which hasn't been written yet. We also want to be able to interpret phase diagrams because after all, the lesson is called phase diagrams. And I know in general we're not the best at diagrams and we don't study them a lot, or we haven't in this course. In science in general, we typically do, but we focus so much on fundamentals in this particular course, and not fundamentals as in easy, but main ideas and mastering them, that we don't get into a lot of the experimental type stuff. Graphs are generally very experimental in nature. There's something in a phase diagram called a triple point, and that's of particular interest to us too. So we'll start here by summarizing. I'm sure at some point in your science career you have seen this. Different states of matter. Of course, you know, I think my 3-year-old son knows the difference between a solid ice cube, liquid water, and he probably doesn't know about water vapor as gas. But we know that clouds are made up of water vapor, little tiny, tiny, tiny water droplets. Humidity in the air is water vapor. We don't often think, however, about how the molecules behave in each of those circumstances, but we can see them pictured here. When we have our ice cubes, our water molecules are they're bound together. In water in particular, we have hydrogen bonding. So when I say bound, they're not actually tethered by covalent bonds, but they're very, very strong hydrogen bonds that hold them together. So all those little molecules are kind of tied together in some way using intermolecular forces, which we're going to talk a lot about. And you can see that that substance is what we would call self-contained. Its shape is definite. The shape of a penny is the shape of a penny, right? It's not going to fill a container. It's not going to take the shape of a container. A solid is discrete. It's definite. And that shape is fixed. It doesn't change unless it's forced to change. So of course you could probably bend a penny. You could melt a penny. Maybe you could break a penny, but that's only with force applied. If the penny's just sitting there on the table, it's not going to change its shape. Liquids, however, are very, very different. Of course. You can see in that picture the liquid water splashing up out of the cup if we shake it too much, or maybe you're in the car driving and you hit a bump and boom, there it goes everywhere. That's because its shape is indefinite. It can be changed without a whole lot of force because liquid flows. And it flows because you can see when we have a liquid, we begin to have that empty space between molecules. Not as much as in a gas, but we begin to see some. There are still intermolecular forces holding those molecules together, but nothing like what we see in the solid samples. So we say generally that the liquids will take the shape of the cup or the glass or the bucket or the pail or the tub, whatever you're putting the water in, but may not fill it necessarily. It's only going to be filled as high as you fill it. So here's a cup of, can you see this? Yeah. I don't know if you can see the top. The glass of water. It's not going to fill that unless I purposefully fill it. Gases, however, always fill the container they're in because gas molecules have a great deal of empty space between them. They bounce around, they're constantly moving. Those collisions are making them fly off into somewhere else. And if we were to take the lid off of this container, they would in fact escape. And we know that in general. If you pop a balloon, here comes all the gas out, right? Or if you opened it up and you could feel the gas coming out. So gases have an indefinite shape. They take the shape of their container always because they fill it, and they will escape if you take the lid off. So their volume is also indefinite, and we've looked at that in Charles's law and Boyle's law. Volume will change according to how the temperature or the pressure is in a given system in a given environment. So what we're primarily focused on is not only these shapes, though I'm going to take just a second. Take just a second to show you them simulated, very basic, looking at how each of these substances behaves. When we look at water and we say it's fixed and kind of rigid and it's a definite shape, what we want you to understand is there still are molecular vibrations. There still is molecular movement, as you can see, going on there, albeit you can see they're very fast, like trembling. But they don't go much of anywhere. They aren't really traveling, and they're pretty tightly bound. When they do move, they move together as a group. When we look, however, at the liquid sample, you can see that those molecules are probably moving with the same speed, the same trembling kind of motion, vibration, and they're attracted to one another, but every once in a while they escape. They get far enough to, as you can see, better take the shape of the container, kind of mold to what they're in. And then finally, when you see a gas, you see this, where you have just molecules bebopping all over the place. They seem to not have a whole lot of attraction for one another because when they do attract, they hit and then they bounce again. Now, what we're primarily interested in talking about phase diagrams is not just what the phases are in terms of how they're arranged molecularly, but also how they change. So again, this is probably 8th, 7th, 8th grade science. You guys know these terms and can relate to them pretty well, but I want to go through them anyway. So at this point, we're going to stop and quiz you a little bit. I'd like you to answer A, B, C, or D. We have the terms evaporation, condensation, melting, and freezing. We're going to go one by one through each of these. So tell me, what is the word that characterizes the phase change from solid to liquid? Okay, and that would be melting, right? So let me do that. One should be, hold on a minute. Okay, so one, solid to liquid, we're looking at C. This is, of course, called melting. And we know that process, again, from when we were probably very young. Now, in the second transition, when we go from liquid to gas, what is that called? We've already used melting, so you don't really have that choice anymore. Yes, so liquid to gas is called evaporation, and that's A. So these are terms you should be familiar with. They're really not new terms. This is where we're accessing your prior knowledge. Number 3, going from a liquid back to a solid. That's called freezing, right? D. And taking a gas, number 4, taking a gas and taking it back to a liquid. This is the process we have when it rains, right? This is part of the water cycle. This whole thing is all part of the water cycle to some degree. Process of elimination, I guess, right? 4 is B, condensation. So these are actually all of our phase changes, and these are going to come into play in the curves on a phase diagram. So it's important that we know what they are and what they describe so that we can identify them on the phase diagram and properly label them. Okay, we also want to understand molecularly what's going on in this process. And before I do, I want to add one to this, and I think the course mentions it, but they don't necessarily come out and label it on any of their graphs. Solid to gas is a transition, and that transition is called sublimation. Sublimation, sorry. And you particularly see this with dry ice. If anybody has ever done like a cauldron at Halloween and gotten some dry ice and you know, kind of smokes, it's a block. We live here by Penn State, so if you go to the creamery and you want to take some ice cream on a trip, take it to a friend, or even take it home if you have a long afternoon, it's very, 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 very cold. To keep your ice cream cold for a long time, they pack it in dry ice, but it never melts, and that's part of the reason it's great for packing such a cold substance, because you won't have a puddle at the end when it reaches those warmer temperatures. It just evaporates directly into a gas. Now there's an opposite process called from gas to solid. You can skip the liquid altogether, and that's called deposition. And that's not something we see nearly as often. It requires very, very high pressures. Okay? Okay, so now we want to understand, combine kind of these two ideas, the molecular basis or description of what's happening in different phases of matter, and then also how those molecules are now behaving when we change our phase of matter. And the course goes on to describe it in terms of intermolecular forces and kinetic energy. And I will focus on that in the lesson tomorrow when we talk about solids and liquids and their properties. For now, however, you're more than welcome to read through this. It's all true and it's all factual and it's all wonderful. I'm going to focus on a simulation, however. Again, this simulation comes from PhET, the University of Colorado at Boulder. They do some wonderful, wonderful things for us. We're going to look here at water. Again, this is the same configuration as I had just shown you, but you can see that now we have an apparatus where we're able to change some conditions. We can change heat and basically a temperature by adding heat and cooling down here. We can change the pressure by forcing, you know, this finger downward and not allowing as much volume for the substance to be in, or we can add more molecules, which would also change the pressure of the system. Okay, and on the right here, you can actually see a phase diagram. I haven't introduced that yet, so we're not going to focus on it too very much. All right, so what we have here is a solid. We're at 157 K. What is that in degrees C? 157. I don't have a calculator nearby. Nope. I can't do that in my head reliably. 157 minus 273 to go back to Celsius is going to be what am I looking at? 157. Minus 116 degrees C. Is that right? I think that's right. Minus 116 degrees C. So that's super duper cold. That's way colder than ice needs to be ice, right? We need ice at 0 degrees C. Okay, so let's add some heat. We're going to just, the way we know most typically to change a solid into a liquid or melt is to heat up the system. So let's do that. We're going to add some fire here. Isn't that cute? And I'm going to go up to 298K. 298K minus 273 is about 25 degrees Celsius. This is what we typically refer to as room temperature. So you can see the molecules begin to change primarily in their motion. So we're going back to kinetic molecular theory, where we say when we change the temperature, molecules move faster. Temperature, remember, is a measure of average kinetic energy in the system. So what's happening here is the kinetic energy has increased. Molecules are moving more quickly, and some of those very, very tight associations or intermolecular forces are being overcome by the general speed and the movement of the molecules. If we take it up even higher, let's go to about 398. That's where I was trying to take it, 398. Well, so we'll raise it 100 degrees K. This is probably equivalent to about 125 degrees C. You can see that now our molecules are moving even faster in some areas. When they escape, they slow down because they're just sort of floating in space without any attraction to anything. You could see their intermolecular forces. This is water, remember, so hydrogen bonding is very, very, very prevalent, very strong. They're just kind of being let go and floating away. And of course, we can increase the temperature even more to exaggerate this effect and see them float all over. Okay, I'm going to reset this quickly. I'm going to give us back water. I'm going to show us what happens with pressure. So can I decrease the pressure? The pressure is at 0 atm. And okay, so I did that wrong. Let's take it back up to 3 something. About 388. Let's take it to 425. 425, 436. We're about at the liquid gas stage here. We're going and we're evaporating. Now we want to go backwards. We want to go from gas to liquid, condensation, and then liquid to solid is freezing. We can do this by applying more pressure to the system. So what we do when we do this is we're actually forcing the molecules together. Okay, and this follows kinetic molecular theory as well. As you increase the pressure or temperature on a system, molecules move more quickly. So actually here, let's lower the temperature. With low temperature and increased pressure, we should be able to reform. Ooh, am I decreasing? I think I was increasing. We should be able to reform our solid slowly but surely. Did you see how that happened? They went from really crazy, crazy, crazy to really pretty still. They're vibrating, but they're still, and you can see they're tethered together practically. And again, we'll go backwards and increase that temperature, and you can see them start to move faster, loosen up, and then get really wild and crazy. And then again, decrease the pressure, decrease the temperature at low, low temperature. And we go back to that solid state, that solid state. I could change my pressure again to move it back up, decrease the pressure a little bit at 227K. Again, that's about room temperature, and you'll see those guys start to loosen up just a little bit. They still look pretty rigid, but that's because the pressure is still decreasing. We need to get an equilibrium there. Okay, so that was really goal number 1. Right? To be able to make sure that we can understand and describe how molecules behave in different states and what's required to overcome the intermolecular forces or make them strong again. Now we need to move on to the topic of the lesson, which is phase diagrams, right? Understanding them, interpreting them, knowing what they mean and what they do. We're going to start here with a general phase diagram. This is not of anything in particular. And what we want you to realize is that what it tells us is the effect of temperature and pressure on phase changes. So primarily using phase diagrams, we can determine where, at what temperature and pressure, water, for example, will be a solid, a liquid, or a gas. So take note that the y-axis is always pressure, always. The x-axis is always temperature, and here we have degrees C, primarily because we understand degrees C, whereas we don't grasp Kelvin. We don't use Kelvin in our daily life. We don't grasp it quite as easily. Okay, so we have three curves. You'll see three curves here. Let's talk first about the red curve. Red curve is called sublimation deposition. You'll see these arrows indicate what's happening on that curve. That curve is indicating where we have a solid becoming a gas and a gas becoming a solid. So this is, I'm going to write here the line or the curve. Both are happening. And that's true for every curve in this entire graph, okay? It's any point, at any point on this curve, we have some solid and some gas in a sample of whatever we have, water, for example. We have some water and we have some gas. Once we cross that curve, you know, once our point is up here, then we are in a solid range. And so this whole area up here depicts some substance as a solid. This whole area over here depicts some substance as a liquid, and then this whole area over here depicts some substance as a gas. And when I say some area, I'm probably skipping through a lot here. What I do mean is that we can pick a point maybe here, and at that point, our substance is a gas. Now, what do you mean, what that point, Mrs. Grosses? Well, we would drop down to temperature and read the temperature in degrees C, and we would take our line over and read the pressure in probably atms or kilopascals, and at that temperature and pressure, our substance is a gas. Now, if it lies on, as I was saying, the sublimation deposition line, it's part gas, part solid. But once it crosses over into the solid area, it is now solid. Okay, so this is all about phase changing and moving and shifting. This is a curve we're pretty familiar with. That's the melting freezing curve. At this point, we have melting. Let me change my pen here so you can actually see. We have melting and freezing points. So at any point on this line is the melting point or the freezing point for this substance. So the melting point you would read on the temperature part of the axis for a specific pressure. Let's say this is pressure number 1, and then we decrease the pressure. If we decrease the pressure, we would read over onto this line. The new temperature and the new melting point or freezing point would be read right there. And of course my lines aren't straight, but you guys understand how to do that. So melting freezing points will change as the pressure changes. Sublimation deposition points will change as the pressure changes. So you can see here it's kind of same effect. And so will the, let me see here. So will the condensation vaporization points. So evaporation and condensation. Vaporization is also called evaporation. Basically the same thing, right? So here, at any point on this curve, we have boiling points. So again, the boiling point can change. The boiling point at this pressure right here would be read at this spot on that axis. But of course, way down here, our boiling point is very different at a much lower pressure. So that's what a phase diagram will show us. Now there are some other important pieces to this, and I've probably run out of colors to highlight. Let's take orange. Orange right here in the middle. This is called the triple point. At the triple point, all three phases exist. So if I highlight just that triple point, now I'm going to go ahead and take my orange crayon here and say this at this temperature, whatever this temperature is, and whatever this pressure is, then I have not only two phases like I would on a line, but now I have three phases, solid, liquid, and gas. And then there's this area up here where we get into sort of a weird state of matter called supercritical fluids. Okay, so now we need to be able to use this. This is where we get into our quizzing portion again. We need to be able to interpret phase diagrams to determine state at all times. This is primarily what's on your quiz. So the question says, this is a very generic phase diagram for some substance X. And here we have real temperatures and we have real pressures, and you can actually go through and determine these. So I'm going to do one for you and model it, and then I'm going to ask you to do the next. So in this question it says, in what phase is substance X at a pressure of 2 atms? So here's our pressure, 2 atms, and 60 degrees C. The very first thing you're doing is finding those points on the X and Y axis. Then you're going to go ahead and follow the vertical line up from 60 degrees on the X axis. And you're going to see where it sort of connects to your line, to one of your three lines. And then you're going to follow the horizontal line across to see where the intersection point is between the two of them. And really what you're aiming for, what you're looking for, is what phase of matter that falls in. Is it in the solid quadrant? It's not a quadrant because there's only three. Is it in the solid portion, the liquid portion, or the gas portion? And in this example, it does end up in the gas portion. So this is how you use a phase diagram to determine what's going on. You can also use it to determine what's necessary to get to a different phase. Well, let's try one of these. So you're going to have to see the pop-up to answer before moving on. Give me 1 second here. Okay, this question says, in what phase is substance X at a pressure of 2 atms and 20 degrees C? Is it a solid, liquid, or gas? If you said it is a solid, you would be correct. We're going to draw our vertical line up and our horizontal line over, and actually that intersection point is right on top of the word solid, so we know for sure it's a solid. So look at those two differences. We're looking at the same substance, in these two examples, the same pressure, 2 atms. Whoops. Sorry about that. Didn't have my pen on. 2 atms in this example, 2 atms. Oh, keep doing it. 2 atms in this example. The difference between them is pressure. In the first example, we're looking at 60 degrees C, we're a gas, and in the second example, we're looking at 20 degrees C, we're a solid. So it crossed that sublimation deposition line from 60, if we were at 60 before, and we went this way. So the process, we would say, that has happened because it has crossed the sublimation. I often say sublimination, which is totally weird. We have crossed the sublimation deposition line. We've gone from a gas to a solid. This is called deposition. So you should also be able to identify the phase change that's occurring. I don't think I have any questions in here like that, but you should be able to do that based on what curve you are crossing. Okay, where's the triple point? Is it point A? Oh, I never put points on here, so let's try this. Is it point A? Is it point B? Or is it point C? All right. So if you answered point C, you would be correct. Again, that triple point is right in the middle where all three of these curves for all the different phases connect. And you have all three phases of substance X. You have a little bit of solid, a little bit of gas, a little bit of liquid. Excellent. What's the triple point of this substance X? So we just looked at the theoretical triple point. Hopefully you know what the triple point is in this case. Here you have to identify the temperature and pressure at which the triple point exists. Alrighty, so here's triple point. We're just going to basically do our work backwards here. We found the point. We're going to drop our line down, and we're going to draw our line across. And of course, I'm not got a steady hand here, so something around 30 degrees C. So we could throw out 60 and we could throw out 0 as options. It's either going to be 22 or 29, and I think it looks closer to 29. And then we could look at the pressure, and of course the pressure is closer to 2. So the correct answer here would be D. At a pressure of 2.2 atms and 29 degrees C, this substance X, whatever it is going to be a little bit of solid, a little bit of liquid, and a little bit of gas. Okay, so where's the fusion curve for substance X? I don't even think I addressed this as the fusion curve, but let's see if you can figure it out. Oh, I didn't do this either. Let's go curve A, curve B, curve C, and each of those letters addresses the line. Okay, this one is curve B. Fusion is about coming together, right? So you should think of that. Come together right now over me. We looked at what each of those phases of matter, states of matter, how they behave. The one in which you have the most come togetherness, the most rigidity, the most interaction, the most connection is a solid. So it would make sense that our fusion curve is going to describe the points at which we're going to that state. So again, the fusion curve defines melting and freezing points. So at any point along that line, at any pressure, you have a melting or freezing point. So the correct answer here was B. Good. A few more examples, then some special stuff we need to introduce. Okay, so using the fusion curve, now we've said, what is the fusion curve? This is the fusion curve. It's always the one that's between the solid and the liquid. Using this fusion curve, you have to decide what would be the melting point at a certain pressure, 3 atms. So go ahead, take a look at that. All right. All right, how do I want to go about doing this? I want to find 3.5 atms. So 3.5 atms are right about there. And I want to draw my line across. Okay? I'm just going to draw across the whole thing just to be thorough. I've got like 4 lines there, but you guys get the idea. I'm going to draw my temperature down. Put my temperature down. And I end up with a temperature in the 20s. So B makes the most sense here. The other option, 52, if you said 52, then you were going ahead and you were dropping your line up here on what's called the vaporization curve. And that's, of course, where we go liquid to gas and gas to liquid. It certainly can be determined from this diagram. This is exactly the kind of thing we determine from phase diagrams. Okay, so vaporization curve, try your hand at this. Is it curve A, B, or C? Hopefully you said curve C, because there we're looking at the difference between a liquid and a gas, and crossing that line would take us from a liquid substance to a gas substance or a gas to a liquid. So this is called the vaporization curve, point C, or this really should say curve C. So now let's find the boiling point. Vaporization curves define the boiling point or condensation point. I don't think we really call it that. It happens so little. We just refer to it as the boiling point of a substance. So again, it depends on the pressure what the boiling point will be, just like we did the melting point piece. So here is a question, what is the boiling point of a substance X at 3.5 atm? So we did just look at what is the melting point at 3.5 atm. We're looking at the exact same diagram. Our melting point was 23. Try your hand at this. I think I gave it to you already. If this is our vaporization curve and this defines our boiling points, then we need to take our 3.5 all the way over to that line and then drop it down. And we find somewhere in the 50s is our boiling point. And the closest we have in our options here is 52. Okay, so if you were able to do that for melting, you should have had no problem for boiling, and this stuff becomes pretty straightforward, pretty straightforward. Try not to say easy ever, because maybe it won't be easy for you. Okay. This is basically, I don't even know why I included this slide. I think this is talking about changes, but that's all phase diagrams talk about is changes. But it might be saying, you know, if you're asked to compare 2 points, for example, in this example, we're looking at one pressure at 100 kilopascals. How do you need to change the temperature to go from a solid to a gas? And in this case, if we said the substance started at 10 degrees C, well, you know that your sublimation curve is right there. And any point along the sublimation curve is going to transition from solid to gas. So you would follow that curve over, much like they're doing here with the dotted lines. And as soon as you reach that, you have, remember, some solid and some gas. So right after that point, any point along this line, you do have a gas. You can increase your temperature from 10 degrees C to 30 to 70 approximately, and have a gas, 30 to 70 degrees C. So these graphs don't only allow you to identify points, single points, or entire areas, but also temperature ranges that you can work in. And why is this important? Well, if you're a chemist in a lab running a reaction and you're familiar with a solvent, for example, and we'll talk about solutions in the next unit, a solvent that you're doing the reaction in becomes a solid at a certain temperature. At room temperature, you want to keep that solvent way higher than room temperature. So phase diagrams are important for us when we're practically doing experiments and we want to avoid the formation of a certain type of phase or encourage that formation too. Sometimes we can only do reactions in the gas phase, for example. Okay, 2 more questions. So this is talking about our changes. What happens when you increase the temperature of substance X from 35 degrees C, so that's right about here, to 65 degrees C, right about here, at a constant pressure of 3.5 atm. So I'm going to draw some thicker lines here for you. We have 3.5 atm. It says what happens. So you're going to pick a description here of what's happening. And just to help you out, you're trying to focus on those 2 points and what has happened as you went from this temperature to this temperature. The options are, you went from a solid to a liquid and finally becoming a gas, so you're melting and then evaporating. It started as a liquid and became a gas, it evaporated. It started as a solid and became a gas immediately, which we would call subliming, or it remained a liquid and did not undergo a phase change. Okay, I see liquid. This point, this first intersection point is almost right on top of the word liquid. So it was a liquid. So it starts as a liquid, and that's the only option. Oh, we have D. It starts as a liquid, B or D. That makes A and C not options. Did not start as a solid, started as a liquid. And it went in this direction. Okay, it crossed our vaporization line, which means it hit the boiling point and went beyond the boiling point. So now it has also become a gas, and it had to evaporate in order to do that. So we could use phase diagrams to determine maybe what has happened as a result of an environmental change we have made. Okay, this is the last one. What happens when you increase the pressure of, okay, wait a minute. Sorry. Sometimes I get ahead of myself. Here we increased, Here we increased temperature and we kept the pressure constant. In this next example, we're asking you to increase the pressure from 1.5 to 3 atm. We're going to keep the temperature constant. So we are going to look right along this line here, 40 degrees C, which isn't much of a line. It's kind of a squiggly, right? We're looking at 1.5 atms. And we're looking at 3.5 atms. And of course, we're looking at these 2 points. So what has happened? When we went from 1, this is our first state, this is our second state, to 3.5, did the gas condense to produce a liquid? Did it vaporize to produce a liquid? Did it condense into a liquid, then freeze to produce a solid? Or did it remain a gas and did not undergo a phase change? Let's see. First of all, this right here is called our vaporization curve. Don't forget your terminology. Vaporization curve. That does not mean that the only thing that happens there is vaporizing. Vaporizing is evaporating. This curve tells us that we can evaporate if we go from liquid to gas, but we can also cross it from a gas to liquid to condense the substance. So it's vaporization and condensation. Of course, oh, wait a minute, that's going across, but in this case, we crossed it vertically, right, like this. And to go from state 1 to 2, we went up. So we started as a gas, we went to a liquid. We started as a gas, we went to a liquid. That gives us most of our options except D, does not remain as a gas. It did definitely undergo a phase change. A says the gas condenses to produce a liquid. B says the gas vaporizes to produce a liquid. So you just have to keep your terminology straight. And that requires you to, again, it seems so silly, but go over and remember and understand these terms. What evaporation is, of course, that is the process of going from liquid to solid, liquid to gas, and then condensation, gas to liquid. So it definitely did condense to go from a gas to liquid. That statement is true. B is not a true statement at all. No gas can vaporize to go into a liquid. If the gas first condensed and then froze, we would have had to take another step, another change. We would have had to be at that pressure and crossed the fusion curve to go between liquid and solid. But we did not do that in this case. So A would be our correct answer here. Okay, I have no hesitation that you guys are picking right up on this. And as always, email me if you're not. It's the first day I'm out, or we're just watching a recording that's going just as long as regular class, even though I don't have you to interact with. I'm pretending I am. One last word, and this is not something I'm going to like really emphasize, but it's important for you to know. In college, you might look at it much more closely. Phase diagrams for water are very different, and they are different in only one aspect. If we look at the phase diagram for carbon dioxide, we have kind of this general curve going upward, our sublimation curve and our vaporization curve, and you can see our fusion curve between the solid and liquid has what we call a positive slope. If we were to calculate the slope of that line or that curve, it would be positive. And you can see in this example for the phase diagram for water, it sort of leans to the left. It's the Leaning Tower of Pisa. It's a negative slope. It goes slightly in the opposite direction, right? This one kind of leans this way, and that one kind of leans the other way. That's referred to as a negative slope. So in water, and this is why we can get all three phases in the temperatures we see, as you increase the pressure, the melting point decreases. So this is our pressure on the y-axis. And if we go from temperature here, I guess we start at 0, right? This is normal melting, 0 degrees and 100 kilopascals, because 100 kilopascals is about 1 atm, and that's normal room pressure for us. If we increase the pressure, we go higher and higher and higher. It's so small of a change, you can see, let me use a different pen color, so small of a change, but the temperature is decreasing. And that's not something that typically happens with solids. Usually, as you increase the pressure, you need to, that's why my simulation wasn't working before. I forgot about water. Okay, let's look at the same thing on this side. If we take some point, okay, here we have about like minus 50 degrees C. As we increase the pressure to about 7,000 something, right, from about 1,000, our temperature has gone up. So pressure and temperature changing, remember, especially with gases. We're not talking about gases here, we're talking about solids and liquids, but remember, as pressure and temperature increase, molecular movement increases. So usually when you increase your temperature, you increase the pressure, you're increasing the temperature because you're increasing molecule movement and speed, and temperature is a measure of that. So typically this is what happens, but with water, this is what happens. And that's just something to point out. Water looks a little different, behaves a little different than is typical. So we can look then, going back at a phase diagram like this, and know that it's water because our fusion curve leans to the left. Okay. That about wraps it up. Hopefully, after 45 minutes, you guys can take away an explanation of molecular behavior in not only single phases, but also phase changes, interpret phase diagrams, know what the triple point, vaporization curve, fusion curve, and all of that is, and can use these. And you guys have a quiz to take on it. So today is Monday, and you're watching this, and you should complete your 1.14 quiz. Tomorrow I'll come to you with another video. That video is on lessons 115 and 116 together. We don't pay much attention to solids and liquids in this unit or in general because gases are so unique and they have so many different and special properties to them. We've talked about solids throughout the course of the course, even though we didn't even realize we were doing it. We talk about bonding and ionic substances and covalent substances and their properties and behavior. So we're going to squeeze those both into one lesson, one 10-point quiz, and you'll be doing that tomorrow. Thanks for hanging with me. And I would love some feedback on this if you guys feel that this lesson was particularly good. Given the fact that we weren't actually together, I would love that feedback. If there's anything you feel that I could change or do differently. Of course, I probably won't be able to do it for this week because I'll make as many of these lessons as I can ahead of time. But feedback for the future is always welcome. And I do appreciate it from you guys in particular because you're my thinkers. Thanks so much. Have a great rest of the week.